We can also use the future value formula to look at the effect that inflation has on our spending power for investments or for monetary amounts. So when we do this, we're going to make a couple of important assumptions. We will assume that inflation acts on or compounds only once per year, so we'll look at an annual inflation rate. So the number of compoundings, little k, is 1. And so therefore the interest rate, which in this case is the inflation rate, is r over k, or r over 1, so it's just r. So our rate of inflation is little I, but it's also little r. And because k is 1, we're talking about the effect of inflation over 1 year. Then little n will be equal to 1 times t, k times t, which is just t. So for the inflation example, the inflation rate is little r or little I, either way, and the total time and the value of little n are equal to each other. So that makes things a little bit easier. So let's see how this plays out. So we're going to start with a really simple example. Let's suppose that the average annual inflation rate is 3%, or little r is 0.03. That means little I is also 0.03. We want to find the cost of a $100 item 30 years from now under this assumption. So you might want to pause the video and see if you can take a good guess, if you haven't already looked at the PowerPoint print slides, about what this will cost in 30 years. I'll give you a second there. All right, let's go ahead and do the calculations then. We're still using the future present value formula, so we have f on the left. The present value, in this case the present cost of the item, is $100, and then 1 plus I is 1 plus 0.03. We're raising that to the 30th power because we're letting interest compound, or in this case we're letting inflation have its effect 30 times. When we do this calculation, we end up with 100 times 2.42726. Now, this 2.42726 is the 1.03 raised to the 30th power. And of course, it's just an approximation because I am reporting these numbers off of a calculator. If you're doing this on homework or on a quiz, you would want to try to compute the entire thing in one calculation at the very top. But this is what we get when you multiply this by the 2.42 number. We end up with 242.73. And so the 2.427 number is sometimes called a growth factor. So this is telling you that the $100 item is growing to be about 2.4 times more expensive in 30 years as it was today. Now notice something. The 2.42 number, the growth factor number, has nothing to do with the original cost of the item. We could have put that amount to be $1,000 or $3, it doesn't matter. What this is telling us is that with an inflation rate of 3%, 30 years from now, that item is going to be about 2.42 times as expensive as it is now. That tells you how inflation is affecting the cost of that item. Here's a visual representation of what we just saw. What you see here is a graph of the value of that particular item over time. And you'll notice that the value starts at $100 on the vertical axis, and then you can see how it grows over time. So what we're doing here basically is saying, let's go out to 30 years, find the point on the graph that corresponds to 30 years, t equals 30 years, and then zip over to the horizontal axis, that's just below 250, and from the previous calculation, we know that's exactly 242.73, at least to the nearest penny. All right, let's play a little game. Let's check your intuition on how inflation can affect your spending power. So let's assume that you have someone who's going to retire, and they're going to retire 30 years from now. And we're going to make the assumption that the total number of dollars in their account is $1.5 million. So that's what the actual statement reads. 1,500, comma 000. So $1.5 million are there. We can think of those as sort of future dollars. And so what we want to do here is assume that we have an annual inflation rate of about 3.3%, which is relatively high, but we'll assume that. And the question that we want to answer is, how much spending power does that retiree actually have when we think about it in terms of today's dollars? So remember, inflation is having an effect on that dollar amount. As it grows over the next 30 years, it's growing in its value, but $1.5 million in 30 years won't buy you what $1.5 million will buy you today, because everything is getting more expensive. So the question is, how much will that actually buy you if you measure it in today's dollars? Is that equivalent to 1.2 million? Or is it equivalent to $2 million? Or is it the same in today's dollars as $850,000? I want you to take a guess. This slide is going to force you to click the forward button before it continues. So take a guess, at least mentally, on how much you think that's worth measured in today's money. This will give you an idea of what effect inflation has on retirement funds. Go ahead and do that and then click forward to move to the next slide. All right, let's check and see how accurate your guess was. Remember, we're assuming $1.5 million is in an account 30 years from now, and inflation has been eating away at the spending power of that amount at a rate of 3.3% per year. So we're still able to use the future value formula that you can see here at the top. F is the amount in the future, P is the current value, or the spending power in today's dollars. 1 plus I is our inflation rate per year, and then N is the number of years that inflation is allowed to act. So let's put the numbers in and see what we get. Here we see on the left $1.5 million. P is unknown, that's the present value, how much it's worth in today's dollars. 0.033 is our interest rate, so we add that to 1 inside the parentheses, and then the 30 years is our power. So order of operations would say do the 1.033 to the 30th power first, and that gives me 2.64856. And this is an approximate value because I'm doing some rounding here. Okay, now look at the formula that you have here. All of the exponents are gone. This is really just a linear equation. Think of putting the 2.64856 in front of the p. So it's like having 2.64856x equals 1.5 million. That's easy to solve. To do that, we just divide both sides by the factor 2.64856, and we get a p-value, a present value, of about $566,346. That is the value of that $1.5 million in terms of what you could buy today. So in other words, if you had $1.5 million in the account in 30 years, you could really only buy the equivalent of about $566,000 in goods today. And that's because you've lost spending power due to inflation. Well, it's quite a bit. In fact, if you look at this number here, this 2.64 factor, because we're dividing by 2.64 here, what we're really saying is that that number, that's sort of like your, that's the factor by which your investment is decreased. So think of that as roughly 3. So basically what we're saying is that inflation cuts by a factor of 3 the value of that investment in terms of your spending power. So that, again, is another great example of how inflation can have a negative effect on your ability to purchase the goods that you need. So even though it seems like you may have a lot of money, you may in fact not have as much as you might think. So let's make a little transition here to a slightly different kind of example. The previous examples assumed what we call discrete compounding, which means you have a finite number of periods per year or a finite number of times that you earn interest in the account. We're now going to assume continuous compounding, where the assumption is that interest is compounded on an ongoing basis or continuously. So you don't have 12 periods, each one giving you a new amount of interest. Instead, interest is just sort of always being generated at all times of the day. Now, practically speaking, if you had this kind of account, the bank would have to do the calculation at some point. What they might do is say, okay, once a month, we're going to do the calculation, figure out how much interest you've earned, but we won't do it under the assumption that you're earning interest 12 times a year, but that you've earned it continuously throughout that month. So the formula then changes, and you end up with, again, still capital F on the left and capital P on the right, so that's still future and present value. Little r and little t still represent what you think they would, rate, interest rate per year, and total number of time in years. But now you have the disappearance of little I and n and k because you don't have to compute the interest rate per period. You don't have little k, the number of compoundings per year. So that formula simplifies to F is equal to P times e to the power RT, sometimes called the PERT formula, because PERT from left to right can be pronounced PERT. The base, E, is sometimes called the natural base in mathematics because it shows up everywhere. It shows up in engineering, biology, mathematics, physics, and in economics. And it is approximately 2.718. Now, word of caution here. This is really important. You don't want to enter 2.718 into your calculator. You need to find the e to the x button on your calculator. And it's often hidden. It's often a different color. So you might see e to the x in blue, which means you have to first hit the little shift or the blue shift button on your calculator. It might be yellow. It just depends on the calculator. So you're going to have to fiddle with this and make sure you understand how to use the E button. But it does have a fixed value just like pi does. And it actually has an infinite number of decimal places that never repeat or terminate just like pi does. So it's a very special number. We're going to use it to compute. And we'll do a quick test here on an upcoming slide to make sure that you know how to use your calculator. So let's do an example. Alright, so let's take a look at an example. Let's suppose $5,000 is invested at a rate of 6% per year. What is the value of that investment after 10 years? Now this example should look familiar because we're using the same numbers that we used when we looked at the discrete compounding case. Now we're just making the assumption that the interest is being compounded continuously. So we start with the formula f is equal to p times e to the rt, and little r you see here is 0.06, so we plug that in, and the time is 10 years, so t is equal to 10. So if you wanted to check that you know how to use your e button on your calculator, you could try to compute e to the power 0.06 times 10, or e to the 0.6. When you do that, you should get approximately 1.82212. So this is a quick little check to make sure your calculator is working correctly, or you know how to use it correctly. So you may want to pause, pull out your calculator, and check that you know how to do that. So this is sort of like our growth factor. It's going to grow at a rate that's about 1.8 times as large, almost 2 times as large. Multiply that by the 5,000, and we get the future value, which is about $9,110.59. Now again, these are approximations based on the fact that I'm doing some rounding in the second line of this calculation. When you're doing homework, when you're doing quizzes, you'll want to try to enter in the first line from left to right all in one entry so that you can round at the very end and you don't introduce rounding error into the middle of your problem. Now, just a quick little note, when we did compounding on a discrete basis, when we had 12 compoundings per year, the number we got was $9,096.98. So the increase from going from 12 compoundings per year to an infinite number or continuous compoundings per year is only around what, $13, $14, $15 here? Not a lot. So you don't gain much from continuous compounding because even though you have more compoundings, effectively the interest rate per period would go down. So if you were to increase the number of compoundings per year, that's great, you're getting interest more times per year, but remember, you would end up on average getting less interest per period. So it sort of doesn't really increase your total future value as much as you might expect. Here's a picture of the future value graph under the assumption that we have continuous compounding. Now notice this doesn't look a whole lot different than the graph that we got when we assumed discrete compounding, and that makes sense based on what we just said in the last slide, which was that you don't get a whole lot more future value by moving from discrete compounding to continuous compounding. So the graph is going to look similar. You'll notice at time 0, the present value amount is the same as the future value amount. That's your initial investment of $5,000. And then as time moves to the right, the future value increases. And what we did was we said, let's take a look at what's going on at year 10. And at year 10, we move over and we see it's just past $9,100 on the vertical axis. So very similar picture because of the close relationship between continuous compounding and discrete compounding, especially if you have 12 or more compounding periods per year in the discrete case. So if you want to look at a picture of this in graphing software like Graphmatica, what you'd want to do is be real careful. It can plot exponential functions. It knows the value of e. So does the Macintosh software called Grapher. But you really have to be careful with powers depending on which software you're using. So for example here, if you're going to enter this into Graphmatica, you'd want to do something like this. You'd want to do y is equal to 5,000 e to the power of 0.06. Now notice that the 0.06, which is the power on the exponent, is in parentheses because you want to force Graphmatica to raise e to that entire power. If you don't, if you use something like you see in the second line, then what Graphmatica is going to do is it's going to do e to the 0.06 first, because it does powers first, then it's going to multiply all of that by x. And that's not what you want. You want 0.06 multiplied by x first, then that becomes the power on the e. So you do have to be real careful if you're putting this into the software. Let's go ahead and do some calculations here and link it back to some previous ideas from earlier in the topic, and then there'll be a video showing you how to do exponential equations and functions in the graphing software.